I sometimes get asked the question, and I've asked it myself, what good is an LMS adaptive filter if you have to know the signal that you're trying to estimate? Well, it turns out there are many ways we can set things up so that we have a signal that can be our target and get something useful out of it. The first we'll look at here is an example application. We'll be using an LMS adaptive filter to invert a system. There are a couple of approaches that we can take. The first approach is something that we've seen before. The idea is that we first identify the system, and then all we're going to have to do now is invert the system. And we'll do that by pulling our W weights out and calculating 1 over WZ. This is a very straightforward approach, but we may have the problem that WZ is non-invertible. If we have zeros outside the unit circle, for example, inverting it becomes an unstable IIR filter. Of course, there are ways to come up with approximate inversions by reflecting the zeros of a FIR filter inside the unit circle and then calculating an inverse, and that'll give us a decent job. Another way is that we could actually use some optimization to come up with a best fit inverse based on our estimate of the filter. But I put this approach up first because it's really not the preferred approach. Using a more direct approach is more common, and that would look something like this. In this situation, we've put the adaptive filter in line with our unknown system, the one that we were trying to invert. And we feed our input to our unknown system all the way down around as our desired signal. But unless we have an anti-causal adaptive filter, it will never be able to learn anything. So we actually insert a delay, z to the minus d. Now choosing this delay is a little bit tricky. This delay is ideally on the order of the same length as the impulse response of our unknown system. We may not know that, and so we'll have to perhaps estimate a larger delay than is strictly needed. But if we're estimating a larger delay, we have the problem that our adaptive filter will need to be correspondingly longer to compensate for that extra delay. So choosing the D from our upper path delay and the length of our adaptive filter is sometimes a little bit of a guessing game or a bit of an art. One disadvantage of this is, suppose our unknown system is simply an FIR system. We may have, in order to invert this, we effectively have to have 1 over that system in the Z domain, which will be an IIR system. But we are approximating our IIR system with an FIR filter. So we know W is going to be stable as long as it converges. What we don't know is how well it's going to approximate the unknown system. One of the reasons this is a bit of a problem is that our unknown system may color our signal significantly. If it colors the signal, in other words, perhaps we put white noise in and what we get out is closer to a pure tone, that means our adaptive filter is going to adapt slowly, and we're going to have a hard time with the coming up with a mu that works. In that case, we will definitely want to use a normalized LMS filter, the NLMS filter, because it takes some of the guesswork out of how to put the mu in this type of a filter. So now that we have the basic structure of a system inversion, let's see how we would actually use this perhaps in a practical application. We're going to look at something called the decision feedback equalizer. The basic idea is we take our input signal, whatever that may be, we encode it, we modulate it, and we transmit it. And then it'll be picked up by a receiver at some distant location. And we get a signal, and I'm actually going to change that because we would like to have this labeled X of n just because we're used to it. Okay, so when we initially send this, we might use something simple like QPSK, where we have 4 different symbols. These symbols are located in the complex plane, and when we transmit them, the polarization is going to give us our real and imaginary parts, and we'll just have uniform amplitude of 1, although in practice we may have many symbols. So that looks good going out. What we get coming back, or at the receiver, usually looks a lot worse than this. First, we will have some rotation of the symbols in this complex plane. So they will no longer be at 1, 1, 0, 1, and so on and so forth. Next, there may be some gain, so they're spread out. Finally, we'll have noise added, and other problems with our transmission, giving us received symbols that are usually something like this. To decode these, one of the things we could do is just look at the quadrant, and we could say if it's in quadrant 1 or the other respective quadrants, we just quantize them to the positions we expect. In practice, this does not work very well at all, and you have many errors in your system. So what do? Well, we have an unknown system. Fortunately, we know how to deal with such things. This is our unknown channel here. What we don't have is this side path that will give us our training data. So what are we going to do? We will have, actually, let me add plus noise. We will have an initial training sequence. We'll call it dn is our, and this is not well, it is transmitted. It is known beforehand at both the receiver and the transmitter. Then it will be transmitted from the transmitter, received at the receiver. So now the receiver knows what that transmitted sequence was, and it also can observe what it actually received. We would like this to be as short as possible because using a channel is using a resource, and we would like to limit that as much as possible. So we will use our initial training sequence to try to train an adaptive filter the best that we can to compensate for our distortion. So this system looks just like we expected it to look, like something we've seen before. The dn is our initial training sequence, and so xn is going to be our filtered training sequence, at least for the first few samples. Once our training sequence is done, what do? Well, we have several options. The first would be what I'm going to call train and hold. So the first step is train until dn ends, and then keep w fixed. There are situations where this works, but they are much less common than the ones where it does not work. So let's look at another approach. 2 would be train on training sequences intermittently. The problem with training intermittently is that we have to interrupt transmission of useful data to resend a training sequence. This would happen if the channel changes, which is going to happen with mobile devices and may happen even with fixed devices. So If you're streaming some data, maybe you're watching a movie, you don't want it to stop every second or every 10 seconds or even every minute to try to send training data. You'd rather have it be continuous. So this is not the best option. Okay, this last one is going to be a better option, and that is going to do decision feedback. So how that works is we're going to have when we're done training, we will hopefully have a filter that is adapted pretty well, at least well enough for this example, that the received symbols are in the correct quadrant. If they're in the correct quadrant, then we just round them to their target positions of 1, 1 in this particular case, or 1, -1, and so on. And then use that as our training sequence. So this way, assume for the moment that we have everything adapted and the channel starts to drift. Suddenly our values are shifting away from where they should be, and to the degree that they are off where they should be, we can update our filter accordingly. So I've modified now this equalizer to show what's going on. We take the output and we quantize it to a valid symbol, and then we use that as our input once the training is over. So we start then with the switch down on the detrain position. Once the training's over, we switch it up to the quantized position. This also is a takeoff point for our equalized output. Finally, I'll put this elsewhere too, but we haven't yet discussed what the complex LMS adaptive filter should look like. In this case, the output is going to be W Hermitian times X. The error is defined as before, D minus D hat. And the weight update is Wn plus 1 is equal to Wn plus mu E conjugate X. So the main things are that the weight is conjugated when we do the initial filtering, and the error is conjugated when we do the filter updates.